Hello everyone, this is Aditya and today we'll discuss the complete quantum mechanics in a one go. So please do like, share, subscribe my channel and please support my channel. And now let's start with the quantum mechanics. So we will start with the introduction of quantum mechanics, that why it developed, and then we will move forward, right? Okay, so let's start. So basically we all know classical mechanics. We have been using it since a long time, right? The Newton's formula. So basically it failed at 2 points, right? The first is when velocity is almost close to the speed of light, and the second for very minute particles like electron, protons and neutrons, right? And other particles too. Just for example, I was saying very tiny minute particles, you can say, right? So for this Einstein had developed relativity, and for this we developed quantum mechanics, right? But what was the need of quantum mechanics, right? We all know about relativity. Maybe if you don't know, I will take another course on relativity, but today our agenda is quantum mechanics, right? So what was the need of quantum mechanics at the first place? Because we had classical mechanics, then why quantum mechanics? Well, let's see. So let's see. For example, there's a particle that is very small, like for example, electron or proton or photon, whatever you can assume, right? So suppose you take a microscopic particle or atomic level particle. By microscopic, I mean that I'm taking some atomic level particle, right? Okay. They're taking some microscopic particle and then you are calculating its position, momentum, and velocity at a particular instant, right? Suppose at t is equal to t naught, right? So just like in classical mechanics, when you calculate for macroscopic particles at suppose t is equal to t naught, you get a specific set of state values. I should have not used that term. You will get you will get some precise values, like you will get exact position, exact momentum, exact velocity, right? But in the case of atomic particles, when you calculate at instant t is equal to t naught, then you won't get, we won't get exact results. There will always be uncertainties, but in this case we are deterministic, which means that classical mechanics is a deterministic physics, right? Is deterministic, classical mechanics. But quantum mechanics on the other hand is probabilistic. What do I mean by probabilistic? Well, let's see. Suppose there's an electron or some tiny particle, some minute particle, and it goes like this. It is going in some trajectory, right? Suppose at t is equal to t naught, suppose at t is equal to t, it is suppose over here, right? But on the other instant, suppose t plus dt, it goes to some other point, right? Suppose over here. So where it will be in that interval, this is a big question. What I mean is that if you have a particle after a dt interval, where it will be, there is no chance to tell. We only have probabilities, right? For example, this is an electron, right? It is over here, and then after suppose time dt, you are asking that where it will be. Okay, so now you get a region. Suppose it can be over here, 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 or anywhere, right? So suppose you now have probabilities that it is 1% chance that it will be over here. Here it is 20%, here it is 65%, and so on and so forth. So it is more probable, let me write it like this, A, B, C, D, E. So it is more probable to find the particle at C as compared to B, and it is very less probable to find the particle at A, right? Because it has a probability of 1%. And if I go out of this region, suppose F, where the probability is suppose 0%. So we are certain that we can't find the particle over here, right? But in this region we don't have any certainty, because over here we know that particle will not be there, but in this region we don't know anything, because particle can be anywhere, right? And I made discrete sort of thing, but it is like a continuous wave. We will discuss it later, don't worry about it. Okay, so basically what is the basic idea is that the quantum mechanics is a probabilistic world, is a probabilistic physics, while the classical mechanics is the deterministic physics, right? And that is the huge difference between them, right? Okay, so let's see a basic experiment to clarify our ideas about the experiments and the ideas that we see in the quantum mechanics. And I'm trying to be a bit fast, because else the lecture will go very big, right? So you have to also maintain a pace with me. Okay, and if I make any mistake, please do comment me in the comment section so that I can improve on that, because basically I'm not well, so that is why uh, there might be some problem that I make some mistake while writing, so kindly bear with that. And if you see any problem, you all can anytime comment me in the comment section. Okay, and I will try to improve that thing. Okay, so now let's see, suppose, and this is a reference sheet which I have written, and obviously I can't provide this because it is for my reference only, like what all topics I need to taught, because there's nothing much written in this. It is just for my reference that what is the sequence and what all things I have to teach, right? That's okay. So suppose you are doing an experiment. This is a glass jar, suppose, and you have filled with water. Okay, this is your air, this is water, and outside is also air, and you are ejecting some photons. I mean, you are throwing some light, laser light, assume some laser you are emitting, and it is going and striking over here, right, on the interface, and some part of it is getting reflected and some part is getting refracted. Okay, is it okay? So we say that the suppose there are n number of photons that are coming. Okay, so we say that there's 20% probability or 20% chance that the photon is reflecting back, and there's 80% chance that the photon is refracting. So what's the problem? Well, if you throw 100 photons, then you are sure that 20 photons will reflect and 80 photons will refract, right? Basic thing. So what's the problem? The problem comes when you take a single photon. For a one photon, you won't say anything, because when you throw a single photon, then there is a chance that there's a 20% chance that it is reflecting back, and there's an 80% chance that it will refract. So you can't say anything, but the experiment is still the same. It means that if you throw a photon, one photon, it goes to the interface and then it refracts. It refracts. Okay, sorry, it refracts. And suppose you send a second photon of the same of the identical properties as the previous one, right? It goes, it strikes the interface, and then it reflects. So what's the difference between these two things? Let's see. The throwing of photon or the emission of photon, right? The emission of photon had the same properties, means it was a similar, it was a truly identical experiment, since the properties of the photon was exactly same, which means truly identical experiments in quantum mechanics may or may not yield or give same results. What it means is that you emitted two photons, means one by one, so one was reflected and one was refracted, and the experiment was truly identical experiment. You did not make any changes, but still due to the probabilities you ended up getting the different results, that one reflected and one got refracted. But in the case of classical mechanics, this statement is truly identical experiment in classical mechanics will yield the same result. It is the condition over there, but in this case it is not necessary, since it is we are dealing with the probabilities, so that is why we are not certain about anything. So that's why the same experiment performed many times will give different results. And that is something really weird about quantum mechanics. I know, I understand it, right? Okay. So this was the basic idea that how quantum mechanics was developed. And now we are going to deal with the Wien's displacement law and other things, because first of all we have to deal with the thermo part, because then only we can understand the development of the quantum mechanics. So let's start with that. Okay. So before coming to the Wien's displacement law, we are going to cover some concept of Kirchhoff law and black body. So we will just quickly go through that. Kirchhoff law. It should be double H. Okay. So basically, what is the idea in Kirchhoff's law? Well, let's see. It states that all bodies emit and absorb wavelengths, electromagnetic waves or radiation, whatever you want to say. All bodies emit and absorb electromagnetic waves at all temperatures at all time. Basically, whenever there's a body, for example, this is a marker, right? So currently it is also absorbing and emitting the electromagnetic radiation, right? And that is why its temperature is constant. Else, if it is only absorbing the electromagnetic radiation, which means its temperature should increase, and if it is radiating only, it is emitting only, so in that case it will be like its temperature should decrease. But we know that its temperature is constant. Anything, your hand, your this watch or whatever thing, everything is all the time emitting the electromagnetic radiation, and it is absorbing also, but still we don't feel it because of this law, because the amount of emitted radiation, the energy emitted is equal to the amount is the energy absorbed. So that is why there is no net change in the energy, right? So that is the thing. Okay, so what is the next thing? Okay, yeah, black body. So notice that in this case there is not 100% emission or absorption, right? And when there's 100% absorption and 100% emission, in that case it becomes a black body. A black body is a body and it has nothing to do with the black color. Okay, kindly note this. So black body is a body which emits and absorbs the radiations, electromagnetic radiation, of course, radiation of all wavelengths. Yeah, I'm not writing the complete thing. Okay, you understand it is wavelength. Okay, so basically it is a body which emits and absorbs all kind of wavelengths, obviously electromagnetic radiation. Okay, so this is the basic idea of Kirchhoff law and black body, and I don't think so that I need to go into much deep in that, because you all know thermodynamics. So that is okay. Okay, and the radiation that is emitted by black body is called black body radiation. Okay, just understand. So now we are coming to the first thing that we have to study thoroughly is the Wien's displacement law. And what is it? We will study it by a thought experiment, because I can't right now do the experiment. If I will get some time, I will try to upload a video on that, or the complete experiment, right? So for now you have to bear with me by thinking about that experiment. Okay, or you can watch it on YouTube. It might be available. Okay, so you all can try it watching it. Okay, so basically what we will do in that experiment is that you take a bulb and then you use a variac. Okay, means you will vary the voltage across this bulb and you will observe the readings. Suppose this is the volt 0, 20, 40, 80, 100, 120, 140 and so on and so forth, right? So suppose you go from suppose 0 volt to 20 volt. So obviously you are basically changing the current across the bulb. Okay, so when you're changing the current, so obviously till some value you won't see anything, you won't see the glowing bulb, but still you are providing the potential difference, so you are providing the current, so that is why you are providing some energy to it. So of course there's some sort of energy that is being radiated by the bulb, but it is not visible to us since it is out of the visible spectra, right? So that is why, but when you come to like 100 watt or somewhat like that, some higher energies, you will start observing that the spectrum is shifting from red to orange and so on, and from orange to yellow or maybe somewhat like that. So basically it is shifting towards the white color. And why it is happening, it will be explained using Wein's graph, right? The graph which we are going to study. Okay, so let's see. So basically, don't worry about the u lambda, I am going to discuss it in some time. Just for now, stop thinking about that. And suppose this is the visible spectra, right? So when you were like from 0 to 20, you went from 0 to 20 volt, then you went to 40 volt and so on and so forth. So in that case the graph, it looked like this, suppose like this, or maybe like this. Okay, but when you, why is it so? Because you have to, this is your lambda is increasing, so that is why when there was low energy, then in that case the photon must also have the low energy, the light must also have low energy, right? Because we can't say right now that is photon or a wave, right? So I will just use the term wave, light. Okay, so basically when we were at low voltages, then the energy of the wave or the light was low. Then when we are going towards the lower, when we are increasing the voltage, then we are moving towards the lower wavelengths, and we had got suppose this type of peak, then we got this type of peak, and in this case we covered the spectra, the visible spectra completely. So the accumulation of these, it gave the white color, right? That is the thing. Okay, and if I have to study it thoroughly, I have to just work on single graph. Okay, so let me erase this stuff and then let me draw it separately. What is it basically? Suppose this is your graph, this is your lambda, and this is a peak value, and you call it as lambda m. So for every corresponding intensities or somewhat like that, for every graph there is a peak value where you get u lambda as max. Suppose for this one also you had a peak, this is also lambda m dash, suppose, and so on and so forth, but we don't need to discuss this one right now. So basically this is something. So at a particular temperature, at temperature T, you will get a particular peak of lambda, right? Because basically when you increase the energy, you are increasing the temperature basically, right? That is, so basically at a particular temperature you will get a particular peak, right? You will get a particular lambda where it will be a peak, right? And from the Wein's displacement law, lambda m into temperature into Kelvin is equal to the Wein's constant, is equal to 2.898 10 to the power minus 3 meter Kelvin. Note this. This is the Wein's displacement law, right? Okay, so far so good. We calculated all this, we calculated the lambda m, right? Okay. So basically what is lambda m? Lambda m is the wavelength in that range at a particular temperature at which the energy is maximum. What is u lambda? You have to see it. So before that we have to discuss something else. We have to see, you have to study Stephen's law, and it states that energy area per unit area energy per unit time, right? That is u. So u is equal to sigma into 10 to the power 4, right? Sigma is the Stephen's constant, right? You all know it. And this is for black body, right? For black body, right? You all should know this from thermodynamics, so I'm not discussing it. And if it is not a black body, then you will multiply by emissivity thing, right? So from that you will evaluate it further, right? But for black body it is sigma into t to the power 4, right? Okay. So basically, when you are calculating the total energy under this, you will have to use u lambda d lambda evaluate from negative infinity or from 0 to infinity, and this is equal to u. So what is u lambda? U lambda is basically so you are getting the total u total, right? The total energy of the wave, the total energy of the thing, the heat, the energy that is radiated, that is the total energy, right? Basically the u total, right? This u. Okay. So what is u lambda? Basically u lambda d lambda, it is telling the energy per unit volume, per unit volume, right? This is the energy per unit volume in the range, in the range lambda to lambda plus d lambda, right? This is the concept. Okay, this is the energy per unit volume in the range lambda to lambda plus d lambda. So using the classical mechanics, we were able to evaluate like the total energy. We were able to explain, we were able to explain the Stephen's law, the Wien's law, Wien's displacement law. We explained it using the classical mechanics. But suppose you assume a particular lambda, and between that you take a very small strip lambda plus d lambda. So what is the energy in that d lambda? That is this, but it could not be explained using the classical mechanics. So for that there's a development of quantum mechanics. It was like the first step towards the quantum mechanics. So let's see how it went. So there were like many debates on this, that how to do all this thing, and it was really a long journey. So it has started now, and now we are going to dive into it. Okay, so let's see. So we are going to start with the Wien radiation law. But what is this? Well, first of all, let's draw that graph again. This is your u lambda, and this is lambda, and you go like this. Okay, suppose this is the graph. Okay, so you need to plot mathematically. You have to find a mathematical equation that why is it so, that which function will define this. So for that there were many debates and many efforts made by many physicists and in their respective fields. So the first one was Wien's radiation law. Wien's radiation law, but it was empirical. It had no mathematical justification, right? So he assumed that the you know what is it is the basically the energy. So if I'm dealing with the I should write nu over here, right? And here okay. So d nu is basically the energy per unit volume in the frequency range nu to d nu, right? Nu to nu plus d nu. Okay, so that is the thing. So he calculated that nu is equal to a nu cube e to the power negative b nu by t, where a and b are constants, right? So it could like explain this graph. It went like this, but then it went like, so it was good, could explain, it was good for high frequencies, but it failed for low ones. Okay, so and the second problem was that it was empirical, so there was no mathematical justification to this. So it was like ruled out for some reasons, for this reason, but still it was a great effort by Wiens to explain this thing. Okay, then came Rayleigh Jeans. Rayleigh Jeans. I'm sorry if I make any spelling mistake. Rayleigh jeans. So Rayleigh jeans, what they did was that they assumed like this. They assumed a box. Suppose a square box, rectangular box, whatever you can say. Okay. So if there is black body radiation inside it, they assume that it is a black body. Okay. So if it is a black body inside, means it is a black body, so it will have black body radiation inside it, and it will go like back and forth. It will interact at different places, go and come back, and somewhat like that. They will be like that. So basically, the black body, the radiation inside that is forming a standing wave. Standing wave, the radiations, right? They're forming a standing wave, right? And they named one standing wave as one oscillator, right? No need to go much deep into it, okay? Just understand. Okay, so they did this. Then they started counting the number of oscillators per unit volume. So number of oscillators per unit volume in the range of nu to nu plus d nu is equal to 8 pi c square by nu cube into d nu, right? This was the thing, sorry. C cube and it was nu cube, sorry, nu square, right? 8 pi nu square upon c cube into d nu, right? Okay. And the oscillators of very high energy, they were least probable to exist in that, right? Obviously, if it is more energy, then it is less chance that that thing will be in high quantity, right? So basically in the middle range it was like high probability, and then as we were going towards the high energies, then the probability was decreasing, right? And the probability, they calculated that probability to find a oscillator of energy E is proportional to e to the power minus e upon kt, where k is the Boltzmann constant and t is the temperature, right? Okay, they calculated it like this. Okay, so now what they did was that they did a very simple calculation, means a basic idea. And what was that? Let's see. They found out the mean of energy. Yeah, that mean of energy, obviously it is equal to the integral negative infinity to infinity of the quantity, or maybe zero, since we are going we are only taking the positive things, right? And obviously energy is positive in this. E into the probability of E dE by integral 0 to infinity of probability of E dE, right? Obviously this is the thing, okay? So this is equal to 0 to infinity of E times e to the power minus E by kt dE, and whatever constant was there, it must have been cancelled up and down, right? Okay, so integral 0 to infinity of the quantity e to the power negative E upon kt dE, right? So after solving this, they got that the mean energy is equal to kt. Okay, this is a mean energy, but you need to calculate the u nu, and u nu, it was the number of oscillators per unit volume, 8 pi nu square by u nu d nu upon c cube into the mean of energy, and mean of energy was kt, right? Kt d nu, right? D nu and d nu gets cancelled, so you get u nu is equal to 8 pi nu square by c cube into kt. But there was a problem. It told that u nu is proportional to nu square, but it is totally wrong, because we know that the graph looks somewhat like this. Yeah, it was okay for small frequencies, but it failed for high frequency, and this is called UV catastrophe, right? This deviation, like it was okay for the low frequencies, but it for high it failed. And the Wayne's radiation law, it was okay for high frequencies, but it failed for the low ones, right? That is the concept basically. So if I draw in a nutshell, it looks like somewhat like this. It is the veins. This is the veins, and this is Rayleigh genes, right? Okay, and obviously this is nu, this is u, nu, right? Okay, this is a basic idea which I'm telling. There are many more things that how they calculate this number of oscillators and all, but for now we just don't need to get into that thing because it is irrelevant for now. And if you all want, I will make a separate video on that how these things were done in detail, because in one shot we have to just cover the complete quantum mechanics by heart. Okay, so we are trying to make things as much crisp as we can, so that it is very easy for you all to understand also, because we don't need to go that much deep level in these things, because there are many more things further in which we have to just brainstorm ourselves. Okay, so let's see the further concepts, right? Okay, and let's see what are the further concepts which we are looking forward. And okay, so there was a problem that we were not getting particularly a nice theory for this. So then came Max Planck. So what was his contribution? Well, so he thought, till that time we were thinking that the light was a wave, right? So he thought that instead of considering them as a continuous packet of energy, as a continuous form of energy, sorry, he assumed that the energy that is transmitted is in the form of a quanta or wave packets or energy packets, which he named as quanta, right? So basically what he did was that he assumed that instead of the integral 0 to infinity e to the power e to the negative e upon kt dE upon integral 0 to infinity e to the power negative e by kt dE, he said don't use this. He said it is for continuous form of energy, but he said if it is in the form of quanta or energy particles, and he assigned energy of a single quanta or a photon as h nu, right? So for n photons it will be n h nu, right? So he said that the mean energy is basically equal to the summation as n goes from 0 to infinity of n h nu e to the power negative e by or e negative n h nu by kt d no d sorry upon n is going from 0 to infinity of e to the power negative n h nu by kt, and we are not going into the calculation, but the final result, it came out to be h nu by e to the power h nu by kt minus 1, and this was the final result which we had got, right? Okay, so it's okay, we got this was the mean energy, and then we got u nu is equal to the number of oscillators d nu into the mean energy. Mean energy now is h nu by e to the power h nu by kt minus 1 d nu, and d nu gets cancelled, and you get this. And to a great surprise, it was actually explaining the graph. But Max Planck was not happy with this, because he was thinking that it is just a mathematical justification which we are trying to make, but it is nothing to do with the physics, because it is just like he assumed that it is just more of a like some fictional thing he assumed. But in the later part he was proved that he was right actually, so we will discuss that now. Okay, but before that, let's see some different from form of this u nu. Let's see. Okay, I hope my board is getting little messy over here. Okay, so you get u nu is equal to u nu, and you multiply by a d nu, you get this is equal to 8 pi nu square by c cube into h nu by e to the power h nu by kt minus 1 d nu, right? You got this? Okay, so you know that C is equal to nu into lambda, right? So you get nu is equal to C by lambda. So you get d nu is equal to negative C by lambda square d lambda, right? So if we have to express u lambda d lambda, u nu and d nu in the terms of u lambda d lambda, you know u nu d nu is equal to u lambda d lambda. But in what reference? You have to multiply by negative C by lambda square, right? So you get this. So if you have to express this in terms of this, just do this u lambda. So if you have to convert, basically if you have to change this to this, you will have u lambda d lambda is equal to 8 pi nu square by c cube h nu by e to the power h nu upon kt minus 1 into negative c by lambda square d lambda, and you remove this d lambda and you get this thing, right? This is okay? Yeah. Okay, so this is the basic definition. Then you can convert, obviously nu is equal to c by lambda. You can put over here and you will get your results, okay? Depending on whatever things, right? You have to substitute over here and over here and over here, right? You will get your results. Okay? So this is the basic idea, okay? Now let's see the second most prominent thing in the history was the photoelectric effect, and the experiments were done on that, but still it could not be justified because while performing the photoelectric effect, basically, one minute. So basically, while performing the photoelectric effect, what happened was that when we were emitting the light waves on the surface of the metal, basically this is your metal and this is your light wave. Notice what I am saying, it is a light wave, okay? So we were emitting some light waves on this, and then for certain criterias there was the emission of photoelectron, and it was noticed that as soon as the photon as soon not photon, because we are talking about light wave, right? So as soon as the light was emitted and when it interacted with the photon, it immediately ejected that. This was a problem because if light was a wave, then it must have taken some amount of time, but in this case it was not. Since the light takes some, if it is a wave, it would take some amount of time to transfer that energy. So this was the first problem, right? And the second thing was that for if we were increasing the frequency by keeping the if we were increase the intensity by keeping the frequency constant, then to whatever extent we increase the intensity for a given frequency, there was the photons were not getting emitted, right? So these things were baffling the scientists, that how is it so, that why is it happening. So from that then came Einstein in 1905, and in his research paper he said that see the light wave as photons, as Max Planck did, and then the things could be explained, because then it will packet of energy, photons, and as soon as they interact with the electron, they will immediately transfer their energy to the electron and then it will get ejected. And he gave the equation that energy, suppose, is h nu. The h nu is the energy of the photon, so h nu, the energy, is equal to the phi, this is the wave, this is the work function, plus the kinetic energy of the photoelectron, right? So the kinetic energy is dependent upon the frequency of the light and not on the intensity. So that is why it proved the particle nature over here of the light. And previously we were thinking that, using in the cases of diffraction and interference and all, we used to think that light is a wave, but Newton had said that it is a particle, and there was a huge debate on that, which we won't discuss right now in this course. So basically, this is the thing. So from that, it proved the particle nature of light, right? And it was really fascinating that how we were assuming the things to be in the wave nature, and it came out to be as a particle nature. And it's really fascinating thing about the physics and quantum mechanics. So I hope you are understood the photoelectric effect for now, and I will make a separate video on photoelectric effect because it requires much more explanation. But this is a just a basic idea that how the things are going, right? This is the work function, and then you convert phi to h nu naught, then it is the threshold frequency in that. You're at hc by lambda naught, then lambda naught is the threshold wavelength, and so on and so forth, right? Okay. There's a setup also which we do, but we won't discuss it in this course right now because it's not of much use. I will discuss it in my next videos. Okay, so let's start with the most significant aspect of atomic structures, that is the Bohr's model. Bohr's model, right? So basically, what was the problem? Okay, let's see. So first of all, we will see hydrogen spectra. Spectra. So the thing was that it was observed that in the hydrogen spectrum, there were only four wavelengths that were emitting, that were coming out, that were 656 nanometer, 486 nanometer, 434 nanometer, and 410 nanometer, and in between them there was no radiation, right? It means it was like discrete sort of thing that only these four were coming out. So it was a big question that why only these. So to explain this, Bohr's model came out, right? Earlier we know that earlier we knew that the electrons are like revolving around the nucleus, but there was a problem using the Maxwell's electrodynamics theory. In that we knew that if electrons are revolving like that, so it will emit their energy in the form of EMWs, and in that case it will come and collide with the nucleus in less than 10 to the 1 negative 8 seconds. Then why atoms are so stable? So to explain that, Bohr's came, right? Okay, so let's see how he contributed in that. Okay, so you all must have learned that in your school time also, that how the things are going, like this is your, he assumed this is your charge, this is Z, and this is the electron that is revolving around this, right? Somewhat like that. Okay, he assumed this. Okay, so suppose there's a electron at infinity, at that point it will have an energy equal to zero. It is obvious. So when you're bringing it from suppose here to here, and then it starts to revolve. So at that point, what is its energy? Its energy is equal to half mv square plus the potential energy. What is the potential energy? It will be, this is a negative charge, so it will be plus some constant 1 upon 4 pi epsilon, and for free space it's epsilon naught k into ze into negative e by r square, and the r is the nuclear radius, right? So you get it is equal to half mv square plus minus kz square by r square, right? This is the concept. Okay, so this is your first equation for now. I'm sorry, I just drew line that like that. I hope it's clear. Okay, and the second equation, that mv square by r is equal to kze square by r, right? Is it okay? Sorry, it will be r, and here it will be r square. Okay, but what are we even calculating it? We are calculating it. So Bohr stated that there are orbits along the orbits in which the electrons are present, and except those orbits the electrons can't be present in between them. For example, this is your first orbit, this is your second orbit, this is your third orbit, and so on and so forth. So between them the electron will not be present, it will be on present in the orbits, right? So that is the basic idea of Niels Bohr, and in that he stated that when the electron is in this orbit, it won't either emit nor absorb any kind of energies, right? And that was a significant role to explain the stability and the spectrum of the hydrogen atom, right? Okay, so basically this is the thing. Okay, so assume that this electron is revolving along this circle with a frequency nu, right? Okay, so basically when you solve this you get mv square is equal to kze square by r. So basically this is equal to mv square, so energy is equal to half mv square minus mv square, which is equal to half negative of half mv square is equal to energy, right? This is the equation, right? And this is the equation that the centripetal and centrifugal forces are being equated, right? Okay, so basically, and now there was an assumption made by Bohr. What was that? When you are bringing this electron from infinity till here, it is emitting a photon, a energy equal to negative n h nu by 2. Why a negative sign? Because the photon, that is the photons which are going, when it is going from here to here, it is being emitting, right? So that photon will have a positive energy, but in the process the electron lost its energy, so in that process, that is why it is negative, right? Okay, this is the energy, that is energy of the electron over here. And why nu by 2? It is because over here there is no energy, and over here there is no photon, and here it is a new frequency. So in that process it is the average nu plus nu, no, nu plus 0 by 2, so it is nu by 2, right? I hope you are understanding. Basically when the electron is going from here to here, it is emitting photons in the form of energy nu by 2, right? So this is the second thing which you are calculating, and this is another equation which you are having. So combining these three, you can end up getting the results which we usually see in the copy in the books, that it is equal to like negative z square m e4 8 n square h square epsilon naught square, whatever, using these equations. Why? You use v is equal to r omega, and the velocity is equal to r omega, and from that you know omega is equal to 2 pi nu, and you can compare this nu with the velocity, it is v. So we get v is equal to r into 2 pi nu, right? We get this, you substitute it over here, you get m into r 2 pi nu whole square is equal to kz square by r, and you have this relation that energy is proportional to nu, and solving all these three equations you will end up getting this thing. Okay, basically you have to eliminate v, r and nu basically to get this relation. Okay, n is the orbit number, okay, over here. So this is how the concept of energy came from this, and from that you can calculate r, and you can calculate the velocity and whatever things which you want to calculate, right? And from all this he came with the relation L is equal to n h bar. What is h bar? H bar is equal to h by 2 pi, right? H is the Planck's constant, right? Obviously you should know that. So L is the angular momentum and is equal to mvr. So generally when we are taught in the textbooks, we are said that it was a postulate of Niels Bohr that L is equal to nh bar, but it was proved afterwards by him in the same research paper. But he assumed this thing, and from that he got this, and from all this he got this actually. So that is the big difference, what we are taught and what is the reality. Okay, so let's move to, yeah, and obviously if you see the delta E, the change in energy, it is equal to minus me4 upon 8 epsilon naught square h square into z square into 1 upon n1 square minus 1 upon n2 square, right? It is like that, and from this you can calculate, you can set it equal to hc by lambda, put n1 as suppose another any quantity, and then you can solve it, right? And in that, and using this you can prove that the lambda, the frequencies and the wavelength which are being emitted is just it is in the form of a discrete value, right? It is in the form of a discrete value. Using this, since n1 and n2 are the integral values, so that is why they are not continuous. So that is why when the energies are being emitted, they will be emitted in the form of a discrete pattern. So that is why we are getting 656, 480, like those values. I don't remember right now. So that is the concept. So now let's do some problems, and then we will come to next part. I hope you all understood the Niels Bohr, and you have to study a bit it on your own, because it's like not much important right now. Whatever thing was required in this, I told, and it was basically a 2D structure of atom, right? Basically, so it was after that it was a huge development in physics, in quantum mechanics, in non-relativistic quantum mechanics, and many more things. So we will discuss everything. Don't worry about it. Let me erase this. Okay. So let's start with some problem sets. Okay. So let's see the question number 1. It states, if lambda is equal to 532 nanometer, then find the energy of electromagnetic wave. So it is very simple. Energy is equal to hc by lambda, and you all know the formula. You can calculate it, right? Okay. Question number 2. You know C is equal to 3 into 10 to the power. Let me write it. H is equal to 6.626 into 10 to the power minus 34 joule second. I did not make any mistake. C is equal to 3 into 10 to the power 8 meter per second, right? Precisely, it is like 299792458 meter per second. But in practical aspect, we assume this, okay? And question number 2, it's a nice question. In a semiconductor, the energy band gap is equal to 1.2 electron volt. Okay, so basically this is your conduction band and this is your valence band, and in this the energy difference is 1.2 electron volt as per the given question. Find lambda max so that electron can go from valence to conduction band. What is that? Well, hc by lambda will be greater than equal to 1.2 electron volt. It's obvious, right? And yeah, 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule, right? Okay, you should know this. So you get hc by 1.2 electron volt is this lambda. What is this? So you get lambda max is equal to hc by 1.2 electron volt. This is how you solve this, right? Because basically you have to provide this much amount of energy to overcome this. Okay. Now let's do some another problem. So the next question states that if temperature of a pan is 300 Kelvin, then find energy of highest, then find the wavelength of highest energy, means you have to maximize the u lambda. So which means that you use lambda m into T is equal to 2.898 into 10 to the power minus 3 meter Kelvin, and from that you substitute T is equal to 300 and lambda m is the wavelength that is the energy is maximum. So you get lambda n from that. Okay, it is very simple. What is question? What is the next question? It states that from the Planck distribution, it is given u nu is equal to 8 pi nu square by c cube h nu by e to the power h nu by kt minus 1, and at lambda m is equal to 500 nm. Okay, you're given lambda m is equal to this. You have to find the value of e to the power h nu by kt, right? And obviously you're given k is equal to 0.027 by 300 electron volt per Kelvin. Okay, you're given this. So how do you evaluate this? Okay. Since you know lambda m into T is equal to the constant is over here, so from that you can calculate the T, right? And now you can write nu is equal to h c by lambda, c by lambda, c by lambda m, or whatever you want to write. Okay, or you can use this relation also. And wait, you have to find e to the power h nu by kt. So h nu by kt is equal to e to the power hc by lambda kt, which is equal to e to the power hc by k into lambda t, and lambda t is the constant itself. So you get e to the power hc by, I should name it like that, some phi suppose. K phi, where phi is the constant, it is 2.898 into 10 to the power minus 3. And hc is also a constant, k is also constant, phi is also a constant. So you will get a constant value and whatever the result you get, right? I'm not worried about the result because it is based on calculation, right? I'm worried about the physics, right? So let's do one more question and then we will move to the next part. Then we will start the de Broglie hypothesis. Okay. So you're given a 1 milliwatt helium neon laser. So you're given a 1 milliwatt helium neon laser, and in that you are said that you have to find how many photon of lambda 633 nm is emitted in length of 1 meter. Well, it's a nice question. So we are given power is equal to 10 to the power minus 3 joule per second, right? We are given this, which means that in 1 second the power transmitted is 10 to the power minus 3, which means since the length is 1 meter, which means in 1 by c, right, it will be 10 to the power minus 3 by c, right? This will be the length, right? In basically this na, in 1 second it is this, and when you divide by the speed of light, the second and second will cancel and you will get a 1 meter length. Okay, so in 1 meter you are getting this. Okay, 1 second or 1 meter, you can say whatever you want to say, right? In c meter, right? So in 1 meter you will be left with this if I say precisely. Okay, so on solving, whatever result you get, you get. So this is the energy. So 10 to the power minus 3 by c is equal to n, the number of photons that is you need to calculate, into hc by lambda, and from that you can calculate the value of n, right? So I have you understood the first part of this one shot, and now we will start with the second part. So now let's start with the de Broglie hypothesis of material waves. So let's start and let's see what is it all about. So de Broglie hypothesis. Okay. So basically we all know that the momentum of an electromagnetic wave is given by h by lambda, right? We all know this. Okay. So what de Broglie said was that instead of writing this, write it like this: h by p. Well, there seems to be no problem. But what he said further was that for any particle that has a momentum, it will have an associated wavelength with respect to that. It seemed really senseless that time because we see electrons, protons, for example, right? And in general cases, we assume them to be as a particle. For example, this equation meant that you, me, and everyone present in this world, in this universe, everyone is a wave, and which seemed to be very illogical that time. But in reality, it is the truth. Every particle is a wave and a particle. It seems really weird, like how? And from here, it arises the concept of wave particle duality, which meant that any material can exist as a wave and a particle both, depending upon the conditions. For example, when we were performing the interference pattern, the diffraction pattern of light, in that we assume that light is a wave, right? Only wave nature can prove that thing, right? But on the other hand, when we were doing the photoelectric effect, in that case, when that is the light was emitted towards the metal plate, in that case it could be proved using the theory of photons, that is the discrete packets of energy. So in that case, in the case of light, it is also wave particle duality, which means the light itself is acting as a wave and a particle both, right? So it meant that electron, basically we will talk about electrons. Electrons should also perform diffraction and interference pattern because it is a particle as well as it should also be a wave, right? And to a great surprise, using the de Broglie hypothesis, using the wave concept, this could prove that why electrons are stable. Obviously, Niels Bohr had proved using his mathematical tools, but using this also we will study further that there's something called wave function, and when you equate these thing where L is the total arc, the total circumference. So in that case, it is a case of a standing wave. So in that case, you end up getting 2 pi r is equal to n lambda. Obviously, you all must have read it somewhere. For example, this is if this is a nucleus and this is your electron, right? So instead of having a circular path, it will have like this, somewhat like this. So it starts from here, it goes from here to here, right? Then it goes from here to here, then it goes from here to here, and then from here to here. So means there are 4 waves being formed in this, and these are 1 2 3 4. There are 4 antinodes over here, right? Sorry, 4 nodes over here, right? So there's n1, n2, n3 where there is no vibration, right? Okay, so this is something which we don't need to discuss right now because for that we have to know wave function. But basically here n is the number, the orbit number, and lambda is this wavelength, right? For now, okay. So before this discovery which was done by de Broglie, there was an experiment being done which was called Davison-Germer experiment to study some properties of electron. We won't discuss about them. And Davison-Germer experiment was performed, and using that De Broglie hypothesis was experimentally verified, and it was really amazing thing because it was a theory, but then it was experimentally proved. And we will discuss Davis-German experiment in detail in some other lecture because it is totally about quantum mechanics. So right now I won't discuss about that experiment. And it was an experiment which proved that the electron was performing actually diffraction, just like X-ray diffraction thing, you know. Uh, X-ray diffraction technique is used to determine the crystallite structures of different substance, of different solid materials, right? But we won't discuss about that. Okay, so let's study the next topic. Sorry. Okay, so okay, so now we are diving to the quantum mechanics finally, and we are coming to Schrödinger wave equations. And from here, the story of quantum mechanics finally starts. I mean, that was the introductory part, and this is where the mathematical part starts of quantum mechanics. So, basically, now here I will introduce you all something which is really going to come in your dreams and will be a nightmare. Psi, wave function. And of course, it can be represented in terms of three dimensions, x, y, and z. But for simplicity, for explanation purpose, I will confine the course in 1D quantum mechanics, right? Okay. At the end, we might see 3D problems in that we will calculate angular momentum and all, but not right. First, I have to introduce you all this term. So psi of x comma t is equal to a e to the power I k x minus omega t. Where is the amplitude? Okay, everything is fine, but why? Okay, so you all know e to the power I theta is equal to cos theta plus I sin theta. You all know this. So basically, psi is built up of two terms. And what are these? The one term over here is the real thing, and the second thing is the imaginary thing, right? And notice that for any wave, for example, electromagnetic wave is equal to E naught, for example, electric field. If I talk electric field component of the EMW, it is suppose cos of kx minus omega t for a wave moving in the positive x direction. So this cos component tells that how the wave is oscillating, right? It is a sinusoidal wave, right? So this also tells how the wave is there, means it tells basically the probabilities. This thing is really important quantum mechanics. Well, let's see first of all that how we are going to manipulate all this and end up getting our equations. Okay, so wave function is basically a technique using which we solve our problems of quantum mechanics. Basically, it is the biggest thing which is required, which is the building block of the quantum mechanics. Without this, you cannot do anything in quantum mechanics. So you have to just remember it by heart, right? Okay. So we won't discuss much about it because right now it's useless discussing about it. So first of all, we have to build some concepts and then we will come to the basic idea of quantum, of wave function. So now how do we derive Schrödinger wave equation? So for that we will derive it in two conditions. The first for a free particle, what do I mean by free particle? It means it is free from all the influences of the universe, means it is isolated, means there is no force, which means its potential energy will be equal to zero, right? So its total energy will be equal to the kinetic energy plus potential, but potential is zero, so we get kinetic energy is the total energy, right? Okay. And what is kinetic energy? It is equal to half mv square. Since we are dealing with non-relativistic quantum mechanics, so we are not going for too high speeds near the speed of light for now. So we will assume this. Okay. So it is equal to p square by 2m, right? Okay. I hope you understood. M square v square by 2m, m and m gets cancelled, you get this. And what is mv? Mv is p and its whole square, so it is p square by 2m, right? Okay, is it okay? So you get kinetic energy is equal to the total energy in the case of a free particle, right? Okay, now introduce the wave function. Psi, I'm not writing the x and t for now, just bear with it, is equal to a into e to the power I of kx minus omega t. So what we are going to do from this? Well, let's see. Suppose if I used to say y is equal to a cos x, suppose, right? So, or suppose omega t, right? Something like that, and assume this is. So what is dy by dt? It is equal to a omega cos omega t. And what is d2y by dt square? It is equal to negative omega square a sine of omega t. So you get d2y by dt square is equal to negative omega square y. So this is the equation of a wave, right? So similarly, we will derive the same thing with respect to psi, right? This is some example, right? Okay. This is just for example. Don't compare it to the physical world or somewhat like that. Maybe it comes, maybe it don't. Okay. So you take this expression, right? Okay. So I need some space, so that is why I have to erase some stuff over here. Okay. So now you have to first of all learn some concepts before coming to the calculation part. Psi is equal to a is just arbitrary constant. It may be used for the normalization purpose and somewhat like that, but we won't discuss right now. Okay. So e to the power I k x minus omega t. I is the square root of negative 1. K is the propagation constant or wave vector is equal to, yeah. And you can also write it like this. Okay, leave it for now. Okay, let me tell you. So lambda is equal to 2 pi by k, right? And lambda is equal to h by p. Well and good. H by p is equal to 2 pi by k. 2 pi by k, right? So you get h by 2 pi into k is equal to momentum. So momentum is equal to h bar k, right? So which means that momentum is equal to h bar k, right? It's something interesting, right? Okay. So what's next? Okay. Sorry. And what is omega? Omega is the angular velocity, 2 pi nu, right? Nu is the frequency, right? And something interesting, omega by 2 pi is equal to nu, and multiply by h, you get h by 2 pi is equal to the energy. H nu is the energy, right? So you get E is equal to H cross omega. So you get energy is equal to H cross omega, right? Okay. I hope you're understanding. And what is the x? X is the position, t is the time, right? Okay. So having said all this, let's express psi is equal to e to the power I of what is k? K is equal to p by h bar x minus what is omega? It is e by h bar into t, right? You will get this thing. Okay. Now what's next? Well, we are going to differentiate, or we can do one thing more. It is equal to e to the power I by h bar px minus et, right? Okay. So now calculate del psi by del x. Since time is also there, so we have to use the del operator. Del operator is used because when we have several variables and we are differentiating with respect to one variable, okay, is equal to a into p I by h bar into e to the power I by h bar into px minus, or yeah, et, right? This is the case. Okay, this is the thing. Okay, now what's next? Let's differentiate it second time. Del 2 psi by del x square is equal to a times, again this thing will come out, p square into I by h bar whole square. And notice that this was psi. This was psi, right? So basically you got del psi by del x is equal to a p I by h bar into psi, and from here you got again a psi. You can evaluate it. So you get del 2 psi by del x square is equal to a p square negative upon this quantity, right? Okay. So now note some expressions for now, and I will write it over here. You solve for p from here, you get p psi is equal to h bar by a. Sorry, a will also disappear, right? Since psi is equal to a times this quantity, right? So it is equal to negative I h cross h bar del psi by del x, and p square psi is equal to negative h square del 2 psi by del x square, right? Yeah. So now let's erase all this stuff and moving to the other part of the calculation. Why I'm going so long method? Because I have to tell something about operators. And what are these operators? We will see soon, right? Okay. Don't panic. So now we are going to see, we got this expression for now. And now we are going to see psi is equal to a to the power e to the power I kx minus omega t. And we wrote it like this. This expression we wrote like this: a e to the power I by h bar into the quantity px minus et. And now we are going to differentiate it with respect to time, and we get a into negative I by h bar into e into, basically you do it, you get this. Okay, so you get e psi is equal to I h bar del psi by del t, right? So you get e psi is equal to I h bar del psi by del t, right? You got this. Okay, and now having said all this, we can compare these two things. How? So for the case of free particle, what was the case? Energy was simply equal to, the kinetic energy was equal to p square by 2m. So you apply this thing in this equation and you get simply p square by 2m into psi is equal to I h bar del psi by del t. And what is p square psi? It is this thing. You get negative h bar square by 2m del 2 psi by del x square. This is equal to I h bar del psi by del t. And this is the wave equation for the free particle, right? Okay. And now we are going in terms of the psi, in terms of the wave function, right? So this is the wave equation, basically the differential equation. And now we are going towards some other case when the forces are being applied, means the particle is having some potential energy. So let's see in that case what is happening, right? So in that case the energy is equal to p square by 2m plus u, right? This is the case. So you are going to substitute that. You get p square by 2m psi plus u psi is equal to I h bar del psi by del t, and you again substitute this thing and you get negative h bar square by 2m del 2 psi by del x square plus u psi is equal to I h bar del psi by del t. And this is your Schrödinger time independent equation. So this is your Schrödinger time dependent equation, right? Now let's see how we derive Schrödinger time dependent equation, time independent equation, right? Okay, let's see. Okay, psi is equal to a to the power I p x minus et del psi by del x is equal to a to the power is equal to I by h bar into p psi. Is it okay? Del 2 psi by del x square is equal to negative p square by h bar squared psi. This is the case which we got from here, right? Okay. And what's next? And how do we prove that thing? We know that energy is equal to kinetic plus this quantity, right? So basically when you use this thing, kinetic energy is equal to p square by 2m is this, right? P square. So you get energy is equal to p square by 2m plus u. So in that case, when you put this thing, this p square psi, you get energy is equal to negative h square by 2m dot del 2 psi by del x square plus u. And this is the Schrödinger time independent equation, right? I hope you are understanding it, how we got Schrödinger time independent equation. Whatever I have just written the acronym for fun. Okay, so I told that we have to do something from this. What something? Let's see. So I wrote p psi is equal to negative I h bar del psi by del t. And now just bear with me and just remove psi from both sides. You get p is equal to negative h bar del by del t. So del x. Well, it seems very senseless. Means what is this? Well, basically it is an operator. And to represent it, I will write it like this: p is equal to this, and it is now a operator, right? Similarly, for energy I can do the same. Energy operator is equal to I h bar del by del t, and the kinetic energy operator, it was p square by 2m, so you have to divide both sides by 2m, so you get negative h square by 2m del 2 by del x square, right? These are the operator, and when you apply them on psi, you get the characteristic. You get this characteristic equation, differential equation, right? So this is the idea. It is telling the linear momentum. It is telling the linear momentum operator, right? I will understand. Okay. And how the linear momentum looks when it is applied, the linear momentum operator looks when it is applied to the wave function, then we will use this equation, right? Well, we will discuss this in the later part of the course, but for now just understand that this is the operator, right? And from when we wrote u into psi, so u is also the potential energy operator which is being applied on the wave function. Yeah, it is really amazing. It means that there is operator for every operation in quantum mechanics, right? For example, we have linear momentum operator, we have energy operator, we have kinetic energy operator, we have potential energy operator, and we have many operators, right? We'll discuss it further, right? Okay, let me erase all this stuff and let's see what we are left with to do next. Okay, okay. Now we are going to start with some interesting concepts, and that is remember in the starting of the video I said that we cannot precisely tell the location and the other quantities in exact 100% precision, which means we will be given some probabilities. So what function is giving those probabilities? And it is the wave function, which means if I draw, suppose this is the wave function, though I can't draw it like this because we all know that it is an imaginary function since it contains the imaginary values. So we can't draw it like this, but it's okay for understanding purpose. So suppose this is your position, and suppose you're given a wave function like this. It peaks, it again becomes 0 at x is equal to x naught. What does it tells? It tells that the particle is exactly present at x naught, which means the wave function is collapsed at that point. No need to worry about that word which I used. I will tell that later. So x is equal to x naught, okay? So it means the wave function is 0 everywhere except at x is equal to x naught. And to represent such kind of function, we use something called the delta function, delta of x minus x naught. And note delta of x is 0 when x is not equal to 0 and is infinite when x is equal to 0, right? This is the case. Similar is the case with psi. It is infinite at x is equal to x naught and is 0 everywhere else. So this is the wave function when position is exactly known, right? Because some quantity x1 to x2, right? And x1 to x2 of psi of x dx, it will be equal to 1, right? Since we have found the particle over just like the delta function, right? Okay, it will not like negative infinity to infinity square term. It is not that, okay? It is different, okay? I will understanding it. So such kind of function does not exist in reality. It is called unrealistic wave function because we precisely found the position of the particle, but we made a big problem because when we found the position of the particle exactly, then it meant that the momentum, the uncertainty in the momentum, we changed it towards infinity, and that's something really mind. How? Let's see. Okay, so now we see another graph it is symmetric everywhere. It is symmetric, 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 right? It is going like this. This is your psi and this is your position. So here the lambda, the wavelength is precise, which means we precisely know the momentum. And to represent such kind of wave function in which the momentum is precisely known, it is known to 100% accuracy, but the in that case we observe that we have extended the wave function towards negative infinity, positive infinity, which means the position of the particle has become infinite, the uncertainty in the position, which means it can be present anywhere but we can't tell anything. So this is also a unrealistic wave function. Such wave function is given by 1 upon root 2 pi h bar. Just you have to know this, okay? E to the power I by h bar into px, right? I hope this is correct. Yeah. And this is the momentum. This is the momentum which we are, okay? This is the momentum which we found out. P naught, since this is precisely known, right? Suppose that momentum is P naught. Okay. So we saw two unrealistic wave functions, which means they cannot exist. Well, why they can't exist? Because there is some condition which need to be fulfilled for a wave function. And what are these conditions? First of all, we will have to look about them, and then we will see that why I was saying that. So condition for wave function for realistic. So we are talking about the condition of realistic wave function. So the first is it should be continuous, it should be continuous, it should be continuous, it should be finite everywhere, and it should be square integrable. Should be square integral. What does it mean? It means that integral negative infinity to infinity psi of x mod whole square dx, it must be equal to some finite value. Well, why is it so? Let's. So now why we were saying that the position and that thing was means they were unrealistic, because if I take the example of momentum one, in that the wave function was sorry, it was equal to 1 upon 2 pi h bar e to the power I by h bar into px, right? So if you take the psi of x mod whole square, it is equal to psi of x into psi star, means the conjugate, the complex conjugate of psi, and for that you have to know a bit of complex numbers. For example, if this is a plus ib, then it's a minus negative ib, it's the conjugate, the complex conjugate of this quantity, right? So basically whatever be the term, it is we call 1 by root pi h bar into e to the power I by h bar into px into 1 by 2 pi h bar root e to the power negative I by h bar into px. Notice that this and this becomes 1. So you are left with 1 upon 2 pi h bar. And if you integrate it from negative infinity to infinity of this thing, it becomes equal to infinity. This is psi of x mod whole square, which means it is not a square integrable. And the same case was with the position thing, right? So that is why I said that it won't be negative infinity to infinity, it is not going to be equal to 1, right? Okay, so from where did the concept of this square integrable came? It came from the Born's interpretation. And what was that? It was let's see 1 minute, let me erase all this stuff, then we will see that. Okay, so now we are coming to the Born's interpretation, right? So suppose you are given a wave, this is your psi, this is your x, right? And this is your wave function, for example. So what is the probability that you will find the particle from this x to x plus dx? That probability was given by psi of x mod whole square dx. This is the probability. And if you have to find in an interval, suppose a to b, you will integrate it and you will get the probability to find the particle in that interval, pa to b, right? Fine, very easy, very simple, right? So higher the probability, higher is the chance that you will find the particle over there, right? Okay. This was the basic idea of Born's interpretation. And notice that integral negative infinity to infinity of psi of x whole square dx should be equal to 1, because obviously the particle will be present in the space itself, right? It will present somewhere in this axis, right? It will present somewhere at least. So the probability is always 1. Particle will be present, na? That is the thing. Okay. Okay, so now we are going towards some very critical topics which require very high amount of concentration and a lots of enthusiasm, for real, not joking. We are coming to something called Dirac notation, but we won't discuss it right now. We will just use its idea of Ket notation, this, and we will be done. Okay, so Dirac notation. Dirac notation. Let me change the marker since I hope that it's not working properly. So we are going to use the Dirac notation. So we are going to use the Ket notation, Ket of P. What do I mean by this? P is the linear momentum. So basically it is telling the state. And what state I am taking? I am taking the pure state. Well, what's pure state? Now you have to understand. Pure state in which we know value to 100% accuracy of some observable, right, of some physical quantity. And mixed state is one in which we don't know value, but we know probability, probabilities, right? So this is the difference between the pure state and the mixed state. So we are finding the wave function, the state, for finding the linear momentum. Means basically it is a pure state of linear momentum. So Dirac notation is this. It is there are two notations in that. So I won't discuss the first one right now because it will be confusing. So that is why I have just used this Ket notation for now, right? Okay. And let's see further. And we don't need to use it right now. It is just I needed to introduce you all. So that is why I told this, but it was not necessary right now. Is equal to 1 upon 2 pi h bar e to the power I by h bar into px. Of course, we had seen this before, right? This is the thing, okay? Now let's see. Okay, now you have to study something called wave packets before coming to this thing. Wave packet, wave packets. Generally, the waves don't extend towards infinity as there will be infinite uncertainty in the position. So that is why it extends like this. Obviously, it is not good to draw it like this. Since the wave function is imaginary also, I hope it should be drawn a bit closer so it looks good. This is your wave packet, and in this basically there is accumulation of many momentum and many positions. Obviously, this is position, this is your x, and this is your psi. So it is a accumulation of many momentum and many positions, right? It is just telling the probabilities, right? And it's really amazing thing. So which means if you accumulate several momentums, you will end up getting a wave packet, several momentum and positions and other physical quantities, and you will get a wave packet, right? So basically, and now we were going to, now we were seeing that we know we will calculate psi of x. For that, this when we accumulate the momenta of all the pure states, momentum of all pure states, we get a wave packet, right? Basically, we will see it. Don't worry about it. Let's see. So suppose we had assumed this ket notation is equal to 1 by 2 pi h bar e to the power I by h bar into px, right? We were having this thing, right? This is the pure state of linear momentum. Those all the pure states, and then we will assume a wave function which is equal to e to the power negative x square by a square e to the power I of or leave it for now because we don't need to use it. Suppose you are given a corresponding psi x with respect to it, okay? So you are calculating the pure states of psi x now is equal to the negative integral negative infinity to infinity of the pure this thing into the pure states of linear momentum into a of p naught d, and this is basically the amplitude, right? We'll see it in some time that what is a of p naught. A of p naught, basically if you take a of p naught and you take its mod and you take dp, so it will tell the probability of having a linear momentum, a particle with a wave with linear momentum dp. What is the probability of having that? And if you integrate, you will get over a region, right? I bear understanding it is somewhat relatable to the wave function itself, right? So this is how you are evaluating. Basically, you are getting psi of x is equal to 1 upon root 2 pi h bar integral negative infinity to infinity of a of p naught e to the power I by h naught into p naught x dx, right? This is how you are evaluating it will be dp, sorry. This is how you are getting the wave function, and the wave function will might be given to you. And how you calculate a of p naught? A of p naught is equal to 1 by 2 root 2 pi h bar negative infinity to infinity of psi of x e to the power negative I by h bar into p naught x dx. And you evaluate this from x1 to x2, from p1 to p2, you get the probability of the momentum. So this comes from the Fourier transformation, which you need to learn. I might take lecture on that soon, but right now you have to understand it. Okay. So basically, what I am shouting over here, because I know it's like going completely out of, it is going like a bouncer. So let me summarize everything. So basically, we are taking. Sorry, I'm not well. That's why. Okay, so we are taking the pure states of the linear momentum, and it comes out to be this, right? And we are assuming a wave function over which we will evaluate it. Okay, since a wave, as I told, a wave is accumulation of multiple pure state linear momentum, right? So that is why we are taking a psi, a wave function, suppose this, whatever, and we are calculating the pure states of the wave function itself, but it's of no use for now because it's useless, right? Not talking about the kit, but right now, just forget this. Okay, forget. You have to see this thing, okay? Because if I tell the other notation also, you all will get more confused, since it is like you don't know anything about notation right now. But basically, the notation are used to tell the states of the particle right now. You just remember this. Forget about the cat notation also. So psi of x is equal to 1 upon this thing into integral this. Okay, you will be given the wave function, of course. So from this, you are creating a wave from the momentum. This is the accumulation of all the momentums, right? So with the accumulation of all the momentum, and this is the probability of momentum of that particular momentum, and you are evaluating it using the wave function, using the Fourier transformation, and the momentum, the integral of this thing over, or basically you forget this integral also. Basically, this quantity is telling the probability of finding a wave with the momentum dp, right? So it's like, it is like a implies b, so b is implying a. It is somewhat like that. I hope it's a bit like they are going together, like psi x and ap means they both are like interchange. It's the beauty of the Fourier transformation. What can I do in that? Okay, so basically you have to understand this thing, and we will do some problems on this, so it will be clear. Okay, so give me 5 more minutes of yours so that we can summarize everything what all we taught just now, and we will see Heisenberg uncertainty principle right now, and then we will do some problems, and then we will start with the third part of this lecture. And in that we will start with the Dirac notation, and in that we are going to study all the concepts that will blow your mind, like finding the color of the cherries, and like why electron can't exist inside the nucleus, and the tunneling effect, and particle in a 1D box, many sorts of things, right? So we are coming to the uncertainty principle, and it states delta x into delta p is greater than or equal to h bar by 2. What is h bar? It is h by 2 pi, right? So this is uncertainty in the momentum, this is uncertainty in the position, right? So basically, what from our two unrealistic wave functions, when we were evaluating them, means when we had plot them, then we have got that we had exactly find the position of the particle, but in that case we made the uncertainty infinite. And when we were finding the momentum, when we were precisely finding the momentum, we had made the wave function for the position as something which is spread towards negative infinity and positive infinity, right? So that is why, if you know the more precisely you know one quantity, the less precisely you will know the second. Okay, So okay, this is okay, fine. Okay, but what is delta x? How do we calculate it? For that, you have to go to the expectation value, and it is called the mean. Simply, you take the mean, and it is the expectation value. Expectation value is basically the integral 0 negative infinity to infinity of x into psi of x whole square dx. Since we are dealing with a particular time instant, that is why I am not writing the time. This is the expectation value. And what is expectation value of x square? It is negative infinity to infinity x square psi of x. For this you have to study a bit of probability, and it is very easy. You all can do it on your own. So you all know variance. Variance is equal to the this quantity, right? And you take the square root, you get the standard deviation. And this is called delta x. This is the uncertainty in the position, right? Now you have understood. And similar is the case with the momentum, but in that case, mean of momentum will be calculated from negative infinity to infinity of p of, here the function is a of p naught, since it was telling the probability. So it is the wave function in the case of momentum. Basically, it is not exactly that, but still for simplicity purpose you can assume. And p square is again this quantity, p square mod a of p whole square dp, right? You got this thing, okay? So again you get delta p is equal to root p square minus delta mean of p whole square, right? Simple. Okay, so this is the uncertainty, what actually we are calculating. Okay, now let's see some more things about the wave function, and then we will do some problems, and then we'll move to the third part of the lecture. Okay, so let's see. State of the particle is represented by wave function. Of course, everything is dependent on the wave function, right? Like the momentum, the position, the probabilities, everything is dependent on the wave function. That is why state, it means that state are basically the physical quantities which we are trying to measure, whether it is a pure state of something or it is a mixed state. Everything is dependent upon the wave function, right? For the case of unrealistic, it was becoming the delta function, and in the case of unrealistic with respect to like the pure state of momentum, it was becoming 1 upon 2 root 2 pi h bar into e to the power I upon h bar into px, right? It was becoming like that. Okay, so obviously this is fine. Okay, the second at a given instant, at a given instant, at a given instant, wave function can be the pure state of a, of suppose a observable a, and can be a mixed state of a. If it is a pure state, then we say that wave function is collapsed. If it is going from mixed to pure state, right? That is okay. And in this case, we find the probabilities, right? Okay. Now the third thing which we need to understand, the wave function. For example, if we are talking about the discrete quantities, it is equal to summation as I goes from some whatever of I phi of I of x, and it is what is this? Well, suppose there is a physical quantity a, and it has the values a1, a2, and so on and so forth, right? So we are talking about the probabilities of finding a, a2, and so on and so forth. So in that case, this is the superimposition thing. Suppose we are superimposing the probabilities in, in terms of psi x, and the probability of finding ai is equal to ci whole square, right? The mod of ci. Okay. Now what is the fourth thing? So for continuous data, psi of x is equal to integral negative infinity to infinity of c of a into phi of a of x dx dA, sorry. Okay, so we are finding this. Okay, so this is what, and the probability of finding a to a plus dA is c of a mod square dA. Remember something, a of p into psi of x dA x, we were calculating it, right? So remember that in that case we were assuming that p over it would be dx, sorry. So in that case when we were evaluating for a as p, so we're having a of p into phi of something like that. This is the concept. Okay, sorry, it will be a only. I'm sorry. Okay, so remember now that sorry, psi of x was equal to 1 upon root 2 pi h bar into integral negative infinity to infinity a of p into e to the power I by h bar into p x d, right? You are having this, so this is dA, this is x, right? This thing. Okay, I hope you understood it, and the probability was this. Okay, a of p whole square dA, right? Okay, so now when we have measured a quantity, so when we measured a quantity, suppose earlier the wave function was like this, it was a mixed state, but after measuring it became a pure state. Suppose this was before, and suppose after that it became the, we precisely measured the momentum, for example. So in that case it became from psi of x to 1 upon root 2 pi h bar into e to the power I by h bar into p of x, p naught of x, since p naught is the precise value. So in this case the wave function collapsed, right? It means the measurements disturbs the system. A basic thing. Obviously, if you change the wave function after measurements, then obviously the system has been disturbed a lot. Okay, so now we will see some problems. So this is the main question, and it will have some bifurcations. Based on that, you will calculate the things. So you are given a wave function psi of x is equal to ea into a to the power negative some a into this quantity plus, suppose this is gamma, plus I by h bar p naught x. P naught is a precise value that is known. It is a pure state of this. Okay. So the first question is that find a value, find a value of a for normalization. For normalization. So what you have to do, basically you have to just integrate it. Okay. So you can write psi of x as a into e to the power negative psi of mod x into e to the power I by h bar into p naught x, right? So when you calculate psi x mod whole square, you get a square to the power negative 2 gamma mod x, right? Okay, and this term will, when multiplied by its conjugate, it will become 1. Okay, so you get basically integral negative infinity to infinity of psi of x whole square dx is equal to negative infinity to infinity of a square e to the power negative 2 gamma into mod x dx. You take a square as a common and it should be equal to 1. Of course, this is equal to 1. And since it is a mod, so mod for x greater than 0, mod x is equal to x, and for x less than 0, mod x is equal to negative x. You break negative infinity to 0, it will become e to the power 2 gamma x. Since x will become negative x, so it will become positive x, right? Dx plus integral 0 to infinity e to the power negative 2 gamma x is equal to 1. And on solving, you get mod of a whole square is equal to gamma. So from here you can get multiple values of a. Mod of a is equal to root gamma. So a is equal to plus minus root gamma. A can be equal to plus minus root gamma into e to the power I theta, where theta can be anything. Since when you take the mod, e to the power I theta will vanish again, right? So that is why there can be infinite possible values, but we are said to find a single value, so we will assume a is equal to root gamma for calculation, right? Okay. Now seeing the next part. Okay, it was an interesting question, and it was easy type only. I won't say that it is very tough, but still for a beginner it is a nice question. Okay, now we have to find the probability of finding a particle in the range in negative 1 upon gamma to 1 upon gamma. Again, you will integrate this negative 1 upon gamma to 1 upon gamma of psi of x mod square dx, and negative 1 upon gamma to 0 of psi of x whole square dx, plus 0 to 1 upon gamma psi of x whole square dx, and you will get the final answer depending on whatever things is required. Okay, so you get C now. And notice one thing, in that case I had used mod of a. Why? Mod of a square in the first part, because it was psi times psi conjugate, right? So it was a into a conjugate, which is equal to mod of a whole square, right? In this I assume that the a can also be a complex number, right? Okay. So let's see the C part, the third part. So we have to show that for a given dp, the probability of finding the linear momentum. Now here comes the question, the doubt which you all must be having, that how to solve this type of problem. It has come, right? And now you will understand complete theory which I have taught. So to find the linear momentum to be in the range p to p plus dp is max at p is equal to p naught. So basically we need to prove that the dp for a given dp, the probability of finding the linear momentum to be in the range, this is maximum at p is equal to p naught. How do we evaluate with respect to this function? Of course, so in this we will evaluate first of all a of p, right? It is equal to 1 upon that constant integral, and we are evaluating with respect to negative infinity to infinity of psi of x whole square dx, right? We are evaluating with respect to this, and sorry, psi of x into e to the power negative I by h bar into p naught into p of x, right? Notice that this is a arbitrary p and this is a constant p, right? Note this, okay? Dx, right? And when you substitute it over here, after solving the things, you will end up getting a of p is equal to 2a h bar gamma upon root 2 pi h bar into 1 by p minus p naught whole square plus gamma square h bar square. This is equal to a of p, right? You have to just substitute the value of psi over here and then just evaluate this integral and you will get this thing. Okay, I'm not going to the calculation part, that is your work. Okay, I am telling the concept, I'm telling the physics, the mathematical part is yours. Okay, so notice that this quantity, if we make p is equal to p naught, we get the minimum possible denominator which we can get. So in that case, if p is equal to p naught, in that case the denominator is minimum. So if denominator will be minimum, so it means that since gamma and this is a constant value, so if denominator is a minimum value, then in that case a of p will be the maximum value. So it will tell the maximum probability, since the probability is dependent upon the a of p whole square. So that is why for p is equal to p naught, we are getting the maximum probability, right? I have you understood this. Okay. So I hope that now you understood that what we were actually doing in that case, right? I hope you understood what we were exactly finding. So sometimes it is very helpful when we draw the graph of this. Of course, we should not draw because it is imaginary thing, so we can't plot it on real numbers, right? But still, for our curiosity, we sometimes can draw this function like this. At p is equal to p naught, its maximum, right? So now let's see. So now let's see this a of p, and this is p, and at p is equal to p naught, it is maximum. And now let's see the fourth part, and then we will end this part and we will start with the last part, and which is completely made up of all the crazy things, right? This is everything we have built, all the tools which are required for the quantum mechanics, and the next is a Dirac notation, and then we will be super ready for everything to tackle in quantum mechanics, right? Okay, the superimpositions of all the states and everything, it is a building block is Dirac notation in that, and all the states and everything, it is really amazing. But first of all, we have to understand what is Dirac notation first of all, that is why. So kindly wait for that. Let's do this question, and in couple of minutes we'll start that. Okay, so find value of p so that the probability of finding, let me erase this, probability of finding finding a linear momentum in the, it is momentum, kindly don't see the writing, it's I'm speaking, that's why. In the momentum in the range p to p plus p dp is 1/4 times the momentum in the case of c, that is of p naught. Okay, so basically a of p dp whole square is equal to 1/4 a of p naught into dp, right? This was the thing, dp and dp get cancelled, so a of p whole square is equal to 1/4 a of p naught mod whole square. And notice that when we calculated that a of p, in that case there was no imaginary term, so that is why we can directly take the square root, the positive root. So you get the probability as a of p is equal to 1/2 of a of p naught, and from this you can evaluate the things. And if you solve, you will get the value of p is equal to p naught plus minus gamma of h bar. Why? It can be over here also, it can be over here also, since it is symmetric, right? That's why. Okay, so with this we come to an end to our part 2nd, and now we are going to start the part 3. So let's have a break. So now let's start with the Dirac notation and let's see what is it all about. We had discussed it like before, the ket notation, the ket symbol, but I had said that forget that for that time, but now we are in the stage that we can discuss the Dirac notation. So let's start with the Dirac notation. So now let's see. Well, Dirac notation is basically used to tell the states of a particle. Suppose in that case we were trying to find the state of the pure state of linear momentum, right? If you remember, we're saying this thing. This was a ket symbol, right? So using this, we are trying to find the pure state of the momentum, of the linear momentum. Okay. So before that, you should know one thing, that you all know what is a state. So we had discussed states before, and if you superimpose all the states, you get means on the superpositions of all the states of all states of a particular physical quantity, it will give a state space, right? And state is represented by a wave function, and the superpositions means the addition of all wave functions, corresponding wave functions, is called wave function space, right? Okay, so basically Dirac notation is used to tell the state of a particle, and the state of a particle is told by the wave function itself, right? This is how the things are going. And now let's come into the notations. So you all know a term bracket. So it is made up of two terms, bra and ket. So this term is represented as this, and this is represented as this in the Dirac notation, right? And these two are used to tell the states of a particle, right? This is called a bra symbol, and this is called a ket symbol, right? And using them, you can tell the state of a particle easily, okay? So this was the basic idea of the Dirac notation, and now we are going to do some operations on the wave function using them. Okay, let me erase this and we'll be right back. Okay, so now let's see the operations on wave function. So one thing you all should know, that the collection of all vectors is called a linear vector space. You all should know this, right? And we will relate these vectors with the wave function, and let's see how it goes. So we are doing some operations on wave functions using the Dirac notation, right? So the first thing is that you know that there is a unit vector in case of the vector algebra, right? And suppose it is represented by E unit vector, right? Okay. And in the case of the wave functions, we have the normalization, right? The normalization, it's just negative infinity to infinity of psi of x, basically psi mod square dx is equal to 1, right? So these are relatable, right? Okay. And now let's see the second property. We are coming to the scalar product. So we define scalar product in case of the vectors as a dot b is equal to a b cos theta, right? You get this? Okay. And in the case of the vectors, in the case of the wave function, you write it like this. Suppose this is psi1 and this is psi2, and you do it the integral from negative infinity to infinity of the conjugate of the first wave function into the second dx. This is your the scalar product in the case of wave functions, right? Okay. and you can write over here also a b is equal to a dot b cos theta, a into b cos theta. Notice a and b, there is no vector sign, so it represents the magnitude, of course, right? You should remember this. This is a basic thing, okay? And notice a is equal to a square mod a square, right? It is obvious, right? And if you apply in this case, you get psi of psi is equal to negative infinity to infinity of mod of psi square dx. So if the wave function is not normalized, in that case you won't get a 1 but a constant finite value. That will be some magnitude, right? And if you divide by that value, then the wave function will be normalized, right? Okay. And let's see another concept. So suppose if a dot b is equal to 0, we say that the vectors are perpendicular or orthogonal basically, right? Orthogonal. So the similar statement exists here also if we say that two wave functions or wave vectors, though it is not right to say wave vectors, psi 2, if this is equal to 0, then we say that these wave functions are orthogonal. Basically the scalar product is equal to 0, right? Okay. Now coming to some really important point which we are going to use, and we will understand all the states which we had discussed earlier, and you will understand everything that why we were doing all that. Let me erase this and then we will discuss. So now we are going to start with the fourth point. It is again the operation thing only. So just like in the case of 3D space, suppose you need to represent a vector a vector. So you can represent it using three mutual perpendicular vectors which have a magnitude of 1, right? So you can choose any three unit vectors which are orthonormal, right? Orthonormal, I mean that they are perpendicular and their magnitude is equal to 1. But in the general senses, we use I, j, k vectors. You know this is equal to ax I cap plus ay j cap plus az j cap. Sorry, k cap. So this is how you represent a vector in the case in its components, right? Okay. Similarly, if you represent multiple states, suppose phi 1, phi 2, we are using the ket state, not the bra symbol over here. It is the ket symbol, sorry, here it said state. So it is phi 1, this is phi 2, and this is phi 3, and so on and so forth, whatever number of states you want to consider. And you can represent, and notice that okay, we have to discuss something over here. After that we will discuss. And in this, notice that if you take the scalar product of them is equal to the scalar product of this, and it will be equal to 1, right? Okay. And if you take their scalar product sum with the other vector, suppose this thing k and j k, it will be equal to 0 because they are mutually perpendicular. So the angle between them will be 90 degrees. So their vector product with their scalar product, sorry, their scalar products become equal to 0, right? So there should be similar case in this also, that if we have this is equal to so on and so forth is equal to 1, and if you take with any other quantity, it must be equal to 0, and this is the condition of orthonormal. Here also this is the condition for orthonormal. Orthonormal. Okay. So basically we say that over here I, j and k are called the basis vector. Why? because based on them we are expressing the whole vector, whole linear algebra, whole linear vector space in terms of these three vectors, right? Similarly, these are also considered as basis vectors, right? And you can represent the whole wave function psi as the sum of their individual components, phi of I of x. You apply here the ket symbol, right? So you get this. And if you remember, earlier we had discussed this, but that time it was like I just discussed it theory wise, but now you have the logic that why we are writing it like this, because ci is just a constant over here which is used for like superposition thing, right? Okay. And this is how I said that this is the wave function and this is the state, and you're just superimposing every state over here, and you are ending up getting a wave function, right? Okay. Ci is basically the component, and notice that here we have three basis vector. So we are talking about 3D space in this case. But notice that in this you can have infinite spaces. It can be 1, 2, 3, and so on and so forth. You have infinite dimensions. So here you are talking about infinite dimensional. Here you have infinite dimension space. And here you have in 3D space, right? Okay. So let's see some other concept. And yeah, if you have to represent this, there is a function using which you can represent. Remember the delta function. But here we are not using the delta function, we are using the Kronecker delta function of ij, delta of ij. What does it mean? Let me tell you. So let me write this as phi, this I and j are just some the arbitrary values over here, like 1, 2, 3, whatever. Okay. So I and j is equal to delta of ij. And what is Kronecker delta? It states that it is 1 if I is equal to j, this case, and 0 for I not equal to j. I hope you are understanding it. And to a great surprise, you will be astonished to know that the Kronecker delta is used a lot in theory of general relativity. We might discuss theory of general relativity in some course, maybe, but for now, you should know that this is known as Kronecker delta. Kronecker delta. Okay, this is a Kronecker delta. Okay. So now let's erase this, and we will recall some old concepts. Okay, let me erase this. So now just recall one thing, that the pure states of the linear momentum we had written as root 2 pi h bar into e to the power I by h bar into p naught x. You had written this, okay? Is it fine? And if you take this as your basis vector and try to form a wave function out of it, let's see how it will look. Like you remember, you had made like this, ci and then pi I, right? You had done like this, or in the case of integrals, you had done like this. That psi of a was equal to integral some c of a into phi of x dA. You were doing like this, if you remember, right? So just like this, you can make for this case also, that psi is equal to integral a of p naught into e to the power I by h bar into p naught x dp naught upon root 2 pi h bar. And this is just a, a superposition of all the basis vectors which are representing the pure states of the linear momentum. And here we have taken a specific value of to find the linear momentum. For example, here it is a p naught, right? and you are integrating this thing from negative infinity to infinity, right? Okay, so basically you are getting this thing is equal to negative infinity. I should remove the cat symbol over here, and here I will write this is equal to a of p naught into the pure state of p naught dp naught, right? This is how you are evaluating this thing. Okay, so let's come over here first of all and let's see something. So suppose if someone says you to find this is your psi of x, but I am not writing it. This is psi of x, remember, okay, psi of x. So since we are calculating at a particular time instant, for example t is equal to 0, right? So now let's see, this is the thing, and now if you are asked to find the value of c of a, how do you evaluate it? Well, c of a is equal to this thing, pi comma c, the scalar product of these quantities. And why is it so? Why the scalar product of them? Let's see. In this case also ci will be equal to this phi I and psi. But why the scalar product of them? So for that we have to come to the linear algebra, that a vector is equal to ax I cap plus ay j cap plus az k cap, right? So if we have to write ax, how you write? You write it like this. You will write I vector and then a vector. Why? Because it is equal to I dot a vector, right, into cos theta. So you get basically a cos theta, and this is the x component of a, indeed. Okay, so that is why c of a and is equal to the scalar product of phi and psi. Why? From this thing, basically you are taking the basis vector which is phi over here, this function, and original function, the original value, that is psi, and then you take the scalar product of them and you end up getting the coefficient, that is the component ax. Okay, similar is the case over here. Okay, so let me erase this thing and let's see that how things are going. So if you evaluate it, you get c of a is equal to the, using the formula, negative infinity to infinity of phi star of x into psi of x into dx, right? So similarly, if you apply here, you get a of p naught is equal to the integral negative infinity to infinity, what is the this psi star, that is the complex, the conjugate of this thing. It is, it is, first of all you write psi of x as it is, and you take the conjugate of this, you get e to the power negative I by h bar into p naught x by root 2 pi h bar dx. And now you know why we were using ap naught as this thing, and from this we arrived over here, and then from here we arrived to this, and from here we arrived to this, and now we have a complete logic that why we were doing all that absurd thing, because it is somewhat related to the linear thing, that linear vector space, we related everything, and that is physics, the relation between the different things. There is a unification of things, right? Okay, so let me erase all this stuff and we will be right back. So now let's do the similar calculation for the position, for the pure state of the position x naught, and we all know that this was equal to the delta of x minus x naught, and this is the delta function, right? And you all know delta of x is equal to 0 for x not equal to 0, and is infinite when x is equal to 0, right? Okay, so this is the pure state of the position where the value of position is x naught. So we will use this and let's form a wave function. Psi is equal to the integral negative infinity to infinity Again we are applying the same thing over here, that this is psi x naught, this is a constant, this is a constant value into the function delta of x minus x naught into dx naught, right? Okay, now if you talk about the states, the value of psi is equal to this psi of x naught into the pure state of x of the position, you get this, right? And again you can solve for psi x naught using the similar relation, that this will be equal to the uh, x naught will this will be equal to the delta x minus x naught. So this was our phi x, because we assumed that this is our basis vector, though there are some conditions which had to be followed, that it must be orthonormal, but let's see, we will see it later, but we are assuming this to be the basis vector. So let's find this the scalar product of with this psi of x. Let's see what we get. We get integral from negative infinity to infinity. What is the conjugate of this? Well, it is a real valued function, so that is why it will have the same value before and after the conjugation. This is x minus x naught itself into psi of x dx, right? Now see, it is dx. Okay, and again depending on the conditions, whatever value you get, so this is how you evaluate this thing, okay, for the pure states of position. Okay, so now let's see some operators we had discussed before, but now we will see in more detail, because we know the bra and the cat symbols. So now we can use the Dirac notation them and come to some crazy conclusions. So let me raise this, then we will discuss them. So now let's see. So we are coming to operators. We have to learn some concepts in that. So again we will write the pure states of the linear momentum is equal to 1 by root 2 pi h bar into e to the power I by h bar into p naught x, right? And suppose if it is a basis vector, so you can set it equal to some phi, right? Some phi of x maybe. Okay, so you set it equal to phi, and then what you do is that you differentiate it with respect to x. You get 1 upon root 2 pi h bar into I by h bar into e to the power I by h bar into p naught x, right? You get this thing? Okay. So notice that this and this multiplied will give p naught itself. So you get del phi by del x is equal to I by h bar into, there will be p naught also, sorry, into phi. So you get p naught phi is equal to the quantity negative I h bar into del phi by del x. And again just remove the phi from here, you get p naught is equal to negative I h bar del by del x. And since it seems illogical, so that is why instead of saying equal to, instead of saying this, you will set it equal to capital P. So basically this is called the linear momentum vector, this is called the linear momentum operator, sorry. So when you multiply this with phi, you get linear momentum. When you multiply linear momentum with phi, you get this. But in this case you are applying the linear momentum operator on the phi or on any wave function. This is called that, suppose if I write p psi, it means that I am applying the linear momentum operator on the wave function, right? So if I say p of phi, then I have to write over a phi, so I am basically applying the linear momentum operator. I am applying an operator on a certain function, right? This is how we say it in the language of quantum mechanics. We are basically right now understanding the language of quantum mechanics, which started from the Dirac notation, and then we are coming to such crazy ideas of how the things are looking. So now let's see some other things. Let's see for the position also. And for position, let me raise this. So now let's see for the position. So for position, it is the operator is the multiplication by position by x. So over here we represent x into phi, where phi is the basis function maybe, is equal to, or basis vector is equal to the position itself, the value of position, into what is this? It is equal to delta of x minus x naught. So notice that even if it is even if you write x or you write x naught, delta of x minus x naught, it will give the same value. So basically x of phi is equal to x naught into delta of x minus x naught. And notice that not all the wave functions or all the basis vectors will satisfy this function, because there's something called eigenvalues and eigenfunctions, which we are going to discuss the next. So don't worry about this. Now we are going to start with the eigenvalues and eigenfunctions. And so let me erase this and we will be right. So now let's start with the eigenvalues, something called eigenfunctions, eigenvalues, eigenequations. Let's see. Okay, I'm not writing the value or function because we will discuss everything together. So notice that when you had written that p of psi is equal to p naught into psi, right? What does it mean? The linear momentum operator is applied on psi is equal to the product of linear momentum and the wave function, right? It is said like this. So over here you are applying the operator on the same wave function by which the linear momentum value is being applied with that. Means if this is the psi, this is also psi, this is psi, this is not becoming phi or any other thing. The functions are same. In such case, we say that this is called eigenfunction, which is a solution to this differential or whatever equation is there, and the corresponding value is called the eigen value. Okay, and whole equation is called eigen value equation. Okay, similarly for the x case, it was psi or x, the operator which is being applied on the delta function is equal to x naught into delta of x minus x naught. So in this case again the function is still the same, so that is why it is also a eigenvalue equation, right? And this is the eigenvalue, this is the eigenfunction or eigenstate. You can say it also as a state, eigenstate, right? So it is really amazing to learn more about them, and let's see how we interpret it further. Okay, so basically whatever we were writing, for example, that let me erase this, then we will discuss. So let me generalize the eigenvalue equations. Suppose you have a observable A, some physical quantity A, which has a corresponding operator, suppose capital A. So capital A into psi, some wave function, is equal to the value, the eigenvalue, into the same function. So it is called the eigen state or function. You can say function also, you can say state also, right? And this is called the eigenvalue. Okay, I hope you're understanding this, and this is the operator applied on this side. Okay, and now let's see some operations on operator. Some operations on operators sounds like funny. Operations on operators. Okay, let's see how is it. Okay, so suppose you are given two operators A and B. We will be dealing mostly with two operators. Suppose A and B are given. Okay, for now just bear with me and assume there are two operators. Okay, so first thing is that A plus B of some function phi or psi, whatever, is equal to this psi what I am drawing, is equal to A of psi, means A is applied on psi, A applied on psi plus B applied to psi, right? Obviously the words which we are speaking, must be very much controlled in quantum mechanics, because I just said A of psi, which is completely wrong. We are applying this operator on this. We are applying B on psi. We have to be very clear with our words in quantum mechanics actually. Okay, and same thing with the product. AB applied to psi is equal to A applied to B applied to psi. So first you will apply B to psi and then you will apply A to psi, right? Okay. And now we will deal with this product thing, how it goes. So we will take this example of the position operator and the linear momentum operator to understand this and understand the concept of commutator. Okay. Let me erase this, then we'll be right back. So let's assume the position operator and the linear momentum operator, for example. So first thing is same. Of course, they must be dimensionally true. So you have to multiply by some dimensions, means some constants with some dimension to this operator and this operator, then you will evaluate. But I am not telling that because you all know how to do that. It's very simple, like any constant, like for example, so that they become dimensionally consistent actually. Okay. So now let's see, suppose this thing is equal to this thing, okay, this psi, and if I write px psi is equal to this thing, okay, but notice that they both are not same. Why? Let's, okay, so x, what is this? This is equal to negative I h bar into del by del x of psi, right? And what is x? X is the multiplication minus ih bar del psi by del x. This is the result when you apply this thing, equation 1. This is your equation 1. When you put the things, you all remember now that p operator is equal to minus h bar del by del x, right? Remember this now? Okay. But now in the second case, when you apply this, p applied to this x into psi, right? This thing, okay. And now you remember now the operation of the position operator, simply the multiplication by position itself, right? That is what we are doing, okay. So this, and now you're applying the linear momentum operator on this thing. So you're getting negative ih bar del by del x of x psi, which is equal to minus h bar into del psi by del x. This thing is fine, but again you will get psi into del x by del x, which is psi, and they both are not equal, right? So you got that p x psi is not equal to this quantity, or basically p x applied on psi is not equal to xp applied on psi, which means that they both are non-commutative. And in the terms of quantum mechanics, how we write it, we'll write it like this. You find xp minus px. So you, the value you got of this quantity xp, you got this, and the quantity you got this. Subtract them and you get I h bar. Solve it, you will get this thing only. And this difference is commutator x comma p, right? This x comma p is equal to I h bar. So this is the commutator of x with respect to p, right? X with p, okay. This is the commutator with x. This is commutator x with p, okay. Basically, not with respect to. I should not say that. And notice that x or xp is equal to negative of this thing. Of course, you can solve. It is obvious. So, what is the need of commutator? Well, if two quantities A and B, the commutator of A with B is not equal to 0, then quantum mechanics states that then these two physical quantities are not possible to predict exactly, like position and momentum and linear momentum at the same instant, at the same time, actually at the same instant, at the same states, we won't be able to precisely predict the both the quantities, and obviously it is the justification to the Heisenberg's uncertainty principle. So if the commutator value is not equal to 0, then in that case we can never find these two quantities precisely, accurately, to 100% precision simultaneously, and there is some uncertainty. But in the case of if they are equal to 0, then in that case we can precisely find. For example, in the case of the kinetic energy and the momentum, because the operator of momentum is this, and for kinetic energy it's equal to h square by 2m del 2 by del x square. So when you apply such thing, you apply psi, then you again differentiate, and then if we basically, it's your homework, you have to check for this is equal to k. So you need to prove this, that they both are equal, which implies their commutator value is equal to 0, which means they both can be predicted and calculated simultaneously with full accuracy, right? It's your homework to prove this thing, okay, using this and this operator. Obviously it is simple, I told the method how to do this, and it's your task to perform it, okay. So now let's see some other thing. So let's see something about n-fold degenerate eigenvalues. N-fold degenerate eigenvalues. Eigenvalue. It states basically, if you are having the operator which is applied to this state is equal to some eigenvalue into the same state. So basically, and if I goes from 1 to n, so then in that case we say that this is an n-fold degenerate eigenvalue. Basically, for the same eigenvalue you are able to find multiple eigenfunctions. Suppose there are n eigenfunctions which you can find, so it is an n-fold degenerate eigenvalue. Similarly, there exists something called non-degenerate generate eigenvalue. This is eigenvalue, okay. Suppose the momentum p of psi, means p applied on psi, sorry, p operator applied on psi is equal to p naught into psi, right? So in that case, there is only one such function, such eigenfunction, which is 1 upon pi h bar into psi into e to the power I by h bar into p naught x, right? And notice that if you multiply it by some constant, suppose a, then also it is the same eigenfunction. There is no change until you change the main function, right? It is like that, okay. Suppose sine and cos, right? Suppose you are having sine and cos. In that case, it is okay. Sine and cos are different functions, so we say that these are two eigenfunctions, right? But in this case, if you multiply by 2, 3, or whatever constant, it is still the same function, right? Same eigenfunction. Let me erase this, and then we will see some other concept. So now let's start with the Hermitian operator. Well, let's see. Hermitian operator. It sounds so scary at the first time, but it is very easy. Let me explain. So basically, suppose you have an operator A, and you have these states, these two states basically, right? You have this. So you take the scalar product phi 1 A, phi 2. This is equal to negative infinity to infinity of phi star, means the conjugate of phi 1, and you will operate this on A of phi 2 dx, right? And now you just bring the operator over here and you apply on phi 1, sorry, this phi 2 is equal to negative infinity to infinity of A phi 1, I mean A applied on phi 1 phi 2 dx, right? So basically first you will do like that and then you will apply it on that, okay? But it's no need because A is the only operator over here, so leave it, okay? So if the scalar product in this case is equal to the scalar product in this case, then we say that they satisfy, they are called Hermitian operator. I mean A is Hermitian operator over here, and there's another way to represent it, phi 1 this and then this, right? Okay, so this is how you represent this thing, okay? And something to be noticed over here, if I take this idea to a bigger scale, you assume psi 1, this phi 1 and phi 2 as psi and psi, and you operate this on the position operator, you get negative infinity to infinity, and you are applying this, suppose on any one of them, you will get x applied on, suppose psi and psi conjugate dx, you get negative infinity to infinity x psi star dx, you get negative infinity to infinity x psi square this. And in fact, when you use the operator as the position operator, you get the expected value of x, of the position, right? This is how you get the expected value. This is the value, this is the expression for the expected value. And for discrete also you can calculate easily, right? Okay, so now let's coming to the some properties of the Hermitian. But before that, I have to tell Hermitian adjoint, and then we will see some properties, and then we are going to see some other concepts. Okay, so let me erase this and then we will move. So now let's see the concept of Hermitian adjoint and some operations on Hermitian operator, and then we will move further. So now we are going to start with Hermitian, I hope my spelling is right, adjoint. Let's see how we calculate. What is it basically? For example, this is phi 1, this is the operator, and this is phi 2. No, not this. Suppose if this is the case, A applied on phi 2 is not equal to A phi 1 is applied on phi 1 phi 2, but there exists another operator for which it's always true that this. Then we say that B is Hermitian adjoint of A, right? And it is represented as A is equal to B is equal to A dagger. This is called a dagger. So B is called A dagger. And the vice versa is also true. Means if this is a Hermitian adjoint, then A will also be Hermitian adjoint. So this also implies A is equal to B dagger, right? Okay, don't be afraid of the some crazy things, the crazy words which are given. Okay, it's just a method to express the quantities. Okay, so let's see, yeah, some operations. Suppose a plus b and you apply a dagger, it's simply equal to a dagger plus b dagger. You can evaluate. It's somewhat similar to matrix. The matrix equation when you solve. A b dagger is equal to b dagger a dagger. It's somewhat when you apply the adjoint, you get still the same result. Somewhat like that. So that's why it's okay. So now let's see some other concept which we need to discuss. And we are almost to the end of this one shot. We have to cover till deep square well potential, I mean the 1D box problem, and then we will end the lecture. And I hope that barrier tunneling effect, I'm not covering that. You may I might cover it in my next lecture, but I've told so many things, so it becomes very easy when you solve it on your own. So I will, so for your understanding purpose, I will do the 1D box problem, but I will not do the barrier tunneling, and I will cover in my upcoming lectures. In one shot I'm not going to cover that. Okay, so I will understand that because it's like getting too big. So you have to also study, so I can't make it too long, right? So basically I'm covering everything that is required in the quantum mechanics, which is a building block for everything. After that, it's just application part which you can do on your own. I hope you're understanding. Okay, so now let's see some concept of variation of wave function with time. It's something really amazing, right? So we have to discuss it. Let me raise this, then we will start with